Let's take a look now at a little more complex phasor problem that involves all elements, including resistors, capacitors, and inductors. And let's say for the sake of this problem that you were interested in the voltage across points A and B. So you have the whole circuit, there's some current flowing through over here, but you actually want to know the voltage across this entire junction. There are a couple ways we can go about this, especially if we think about this in terms of an old resistor problem. If we want to know the voltage AB, then as a sort of first order problem, we could go about solving the current through the resistor, and then I times R, and that gives us the voltage across the capacitor and the inductor. So approach number one would be to find one of the branch currents and either multiply by the resistance, the impedance across the resistor, or figure out the other current and multiply by the impedance across the capacitor and the inductor. Step number two actually could even be to transform this circuit and take it from something that was a current source in parallel with a resistor and transform it into a voltage source in series with the resistor. And so in this way, all of our elements would end up being in series, and we would just simply find the total current and then find the current across these two items. Either method really works. We're going to start with method one here because it's the most straightforward and will give us a little bit of practice. But again, you can use any circuit solving technique that you want to go about solving these kinds of problems. As the first step in our AC problem solving process, we need to transform all of the elements in our circuit into their phasor domain equivalent. And so two things are important when we look at this current source. First is that it is represented by a sinusoid rather than a cosine. So if you remember back to our assumptions, we are going to assume that all of our circuits are a cosine reference. So we're going to have to transform this to cosine. And second, we need to make sure about the units of our source. And this one in particular is listed in milliamps. Why is it listed in milliamps? Probably because the book wants to trick you up. But again, just to make sure that if we can keep all of these in milliamps, all of our answers are going to be in millivolts. And we'll just multiply or divide by 1,000 to move between the two different unit systems. So for our first step, we're going to transform this into a cosine reference. So this becomes 35 cosine 300t, and then you subtract 90 from the phase, and so this becomes minus 105 degrees. And representing this as a phasor would be 35 e to the negative 105 degree j. And again, in our phasor transform, this amplitude does not, or excuse me, this frequency does not play a role, but we'll use it when we transform our phasors. And the phasor for our resistor is just R, and for this particular problem, R is 80. The phasor for our inductor is JWL, which will be J times our 300 radians per second frequency, and L for this particular problem is 15 millihenries. So our final result right here is 4.5 J, and for this particular problem, we will represent it as this vector quantity there. Finally, for our capacitor, it's negative J over WC, which would be negative J over 300. And our capacitance for this particular problem is 200 microfarads. And our resulting value for this is negative 16.6 J. And we can also represent this as 0, negative 16.6 repeating. So again, we can take out all of our traditional components here and turn them into their phasor equivalents. And now we can perform our original circuit analysis as desired. And again, we want to know what the voltage is across here. Again, that was points A and B. And so we can go about our work by finding either the current through the resistor branch or the current through the inductor and capacitor branch, and then multiplying by either impedance. Honestly, the easier route here is going to be to find the current through the resistor. And so in that way, our AB voltage would be the current through the resistor times the impedance across the resistor. And again, with this just being 80, that's a rather straightforward function. So in the next slide, we're going to figure out how to find this current. And again, it'll be a rather simple explanation because this will again be a current divider. With all of our elements of the circuit converted into phasors, we can go about finding the current through this resistor. And the current through the resistor is a current divider equation. And so we can take the phasor of our source and multiply by the other impedances in the circuit. And so this would be the impedance of the capacitor and the inductor over the sum of all of the impedances, so the resistor, the capacitor, and the inductor. And if we go about plugging our values in, we can have the phasor of our current source here as 105 degrees J, negative 105 degrees J. ZC was negative 16.6 J. The impedance of the inductor was 4.5 J. And then again, we're going to just add all that stuff again, but simply add in the resistor into our equations. Now, again, we're again fixed with the challenge of this is in polar, this is in rectilinear. And if you've got your calculator with you, you can plug all these in with the various units, and you will get either the appropriate vector or the appropriate polar coordinate system. But either way that you enter it, the result should be, the value of this should be negative 5.23 plus 0.58 J. And again, remember, because we started this original problem in milliamps, this result right here will be in milliamps as well. But this is the phasor form of the current running through the resistor. In the previous problem, we found the current passing through the resistor, and we did that because our overall goal was to find that this voltage out here, the voltage across basically the entire circuit, and the voltage supply. And so to do that, we wanted to know that this voltage right here is equivalent to the current flowing through the resistor times the impedance of the resistor itself. And from our previous circuit, we found that the value of the current through the resistor was negative 5.23 plus 0.58 J. And we know that the phasor for our resistor is 80. And so honestly, we can just multiply these two quantities to get our final voltage, which will be negative 418.4 plus 46.6 J. And if you remember when we found this current right here, we found that this current was in milliamps. So that means that right now this is a millivolt result. And so if we want to change this into the volts, we'll just divide everything by 1,000 and have negative 0.418 plus 0.0466. So, I mean, this is the answer we're looking for. That is the final vector quantity. But what we want to do after the end of this is convert this back into the time domain. It doesn't do us a bunch of good when it's a vector, and we really want to know some time domain expression. And so we can transform back and forth between the polar domain and find this value right here, 0.421 e to the negative 186 degrees J. And again, if you're asking yourself, well, how the heck did he do that? Remember, if we plot this vector right here on a two-dimensional coordinate plane where we have our real parts and our imaginary parts, we would start by having some negative value here at 0.418. That's a negative component. We'd have some slightly positive component at 0.0466. And we'd be looking for this object here. We'd be looking for its angle, which would be right here. So that's the angle. And then we would be looking for the object's length, which would be right here. And it has a length of 0.421. And again, you might say, well, why is this angle negative? Because actually it's measuring the angle all the way back here. This is the actual angle that's being represented in this expression. So finally converting this back into the time domain, This should be 0.421 cosine, and our original frequency was 300 radians per second, t minus 186 degrees. So this is a long sort of problem-solving process, but it's the challenge is really in the moving from the time domain to the phasor domain and then backwards. In the end, it's all the same circuit-solving techniques, but then there's the hassle of moving between the different domains. And in the next video, I'll show you how to do all this in MATLAB, so it'll make a whole heck of a lot more sense.